Hello everyone, welcome to my youth programming club. Today we will be solving another daily Leetcode challenge, and the challenge name is find critical and pseudo-critical edges in minimum spanning tree. So given a weighted undirected graph with n vertices from 0 to n minus 1 and an array edges where each array in this 2D array edges will represent the edge between the vertex AI and vertex BI, and this will be the weight of the edge. So for example, 1D array inside the edges array, 2D edges array is given like this. So these two will be the vertices or say nodes, and this will be the weight of the edge between them. I hope you are able to understand what the program statement is saying. So it further says that it represents a bidirectional and weighted edge. So the edge that will be found between AI and BI will be a bidirectional edge. It means that you can go both ways, left to right and right to left. A minimum spanning tree is the subset of graph edges that connect all the vertices without cycles and the minimum possible total edge weight. So let's consider a graph. For example, 1, 2, 3, 4, 5, 1, 2, 3. So what will be the spanning tree of this graph? It will be 1, 5, edge weight is 1, then the smallest edge weight is 2, then after 2, which is the smallest edge weight, it is 3. We can add 3. Now after 3, which is the smallest edge weight, it is 4. But if we add 4, it will be unnecessary because all the vertices are connected. Also, it will result in a cycle. For example, if let's say it was not 3, it was let's say 1. Let's say you decided to take this edge first, and now this being a smaller edge, you decide to take this. So it will result in loop also, and since we have got our edges to be connected, so it is not required. So what we will do is we will pick the minimum weight edge and include it in the minimum spanning tree formed till now. If the addition of edge does not result in a or do not result in a cycle. Does not result in a cycle in minimum spanning tree. So this is how you will be constructing the minimum spanning tree. So the goal of minimum spanning tree is basically all the edges should be connected, all the edges in the graph, and the weights of the edges, sum of weights of the edges should be minimum possible. So sum of weight of edges should be minimum and all the edges should be connected. So this is what a minimum spanning tree of a graph will be. So let's move back to the problem statement. So what you have to do is you have to find all the critical and pseudo-critical edges given in the minimum spanning tree. An MST edge whose deletion from the graph would cause MST weight to increase is called critical edge. On the other hand, a pseudo-critical edge is that edge which can appear in some MSTs but not all MSTs. So what the problem statement is saying is we have to find two types of edges. Critical edge. Basically, if you remove this edge, let's say you delete this edge from the minimum spanning tree, then the weight of MST will increase, or the number of nodes in MST will decrease. If either of these conditions happen, then this is a critical edge. Else, for a pseudo-critical edge, nodes, if we decide to remove this edge, the number of nodes in MST will be same also, and weight of MST will also be same. This MST that we are talking about here are the MSTs that will be formed after removing these edges, critical edge or say pseudo-critical edge. So I hope you are able to understand what are critical edge and non-critical edge, pseudo-critical edge is. So we have to check for these conditions. If the removal of a edge results in the decrease of weight of MST, increase in weight of MST, or the number of nodes in MST decreases, then it's a critical edge. And if the number of nodes in the MST will also will remain same and weight of the MST will also be same after edge removal, then this edge is called pseudo-critical edge. I hope you are able to understand. So now let's move to the constraints part. So what you have to return is find all the critical and non-critical edges. So you have to give the indices of those edges. You can return them in any order. For example, this two here represents the critical edges and this represents the pseudo-critical edges. So this is how you will be returning, and the indices can be any order you may like. So let's move towards the constraints of the problem. So the length of the graph here is pretty small. It's of order 10 raised to power 2, and the edges, number of edges length is of this order, minimum of n order of n square or 200, and edges length, each 1D array in the edges array 2D array is of length 3, and the value of each node will lie between 0 to n, and the weight of the nodes will lie between 1 to 1000. So all the pairs that will be given in the edges array, 2D array, will be distinct. So there will be no repetition of pairs of nodes. So these are the constraints. Now before proceeding to the solution, you should be familiar with the following topics. First will be what is a minimum spanning tree. Second will be ways to generate minimum spanning tree. So particularly, there are two ways. One is Prim's algorithm. Another is Kruskal algorithm. Pardon me if some spelling is incorrect. I hope it does not affect your understanding of the problems approach. So ways to generate or algos to generate MST. Then we will be selecting one of these two. Kruskal forms the minimum spanning tree with the help of edges. Prim's forms minimum spanning tree with the help of vertices. So we are interested in the edges. So we will be taking the Kruskal algorithm, and the time complexity of this Kruskal algorithm is E log E, order of E into log E. So E here is the number of edges. So just to give you an idea what will be the time complexity. And the third part will be disjoint set union. This particular thing, this particular data structure also is used to implement this Kruskal algorithm for implementation of the Kruskal algorithm is nothing but this selecting a minimum weightage and adding it to the minimum spanning tree form till now. If the addition of that as does not result in a cycle in the minimum spanning tree form till now. So this is what a Kruskal algorithm is. So that's these are the three prerequisites that you must be knowing before proceeding further towards the solution. I will be providing links for all these, and it is a great opportunity to learn you for you to learn about those you who are not familiar with these concepts. Meaning what a minimum spanning tree is, Prim's algo, Kruskal algo, their differences, and particularly this data structure, disjoint set union. So you will get to learn about these two and three things, which will be great learning for you if you are new to them. You are learning multiple things in a single problem, so it's a great problem. So without further ado, let's move it towards the solution of the problem. So what we will be doing, we will be sorting edges based upon their weight in ascending order. Why we are sorting the edges based upon their weight in ascending order? Because here we require the minimum weight edge, and we will include in the MST being formed till now if the addition of the particular edge does not result in a cycle in the MST form till now. So this is the reason. This is nothing but Kruskal's algorithm. So firstly, we will be having the edges sorted according to their weights in ascending order so that we can pick the minimum weight edge. And Then we will check form a minimum spanning tree with the help of MST, with the help of Kruskal's algorithm. Why we are picking Kruskal algorithm? Because it deals with the edges to form the minimum spanning tree, while the other one, its counterpart, Prim's algorithm, it uses vertices to form the uh, minimum spanning tree. So it will give you a very little control over the edges. It will give you very little control over the edges. Basically, what we will do is uh, we will be forming a MST first with the help of Kruskal algorithm. Then what we will do after once we have formed the MST, we will check what is the weight of the MST. Store the weight of MST formed. Let's call this original weight. Then what you will do is for each edge, you will be doing two things. Try to remove this edge and form my MST from remaining edges. If let's say you form this MST and the weight of this MST, let's call this new weight, happens to be larger than the original weight, or the number of nodes in MST, new MST, this indicates the number of nodes, happens to be lesser than the number of nodes in the old MST. Which is the old MST I am talking about? This is the old MST that we have formed in the previous step. So if any of these is true, then you will consider that as a critical edge that you have just removed. So this will be a critical edge. And if neither of these conditions satisfies, then you will check for another condition, which will be let me quickly change the color. Forming AMST with the current edge being considered and all other remaining edges. If let's say for this MST, let's call this new MST also. Neither of these conditions satisfies. It means that the new weight of this MST remains same as the old weight, and the number of nodes in this MST is same as the number of nodes in the old MST. Then these will be pseudo critical edges. Pardon me if some spelling is incorrect. I hope it does not affect your understanding of the problem. Problem solution. Pseudo critical edge. So basically, for each edge, we'll be doing these two things. And let's say there are e number of edges. Then for each edge we'll be doing this, forming these two operations. Basically, in this step of doing these two operations, we will be using disjoint set union. So, as I told you, union find operation in the disjoint set union takes e of log e time. So, in nutshell, the time complexity will be e square log e, which can be approximated to e square, or if you want to take this factor also, let's call this alpha, then it can be e square alpha, or you can take it as it is. It's up to you. So this will be the time complexity. So since now e is 10 raised to power 2, so the number of operations will be these. These operations are lesser than 10 raised to power 8 operations allowed in 1 second. So those of you who are new to this limit of operations allowed in 1 second, basically if the number of operations in your program exceeds or become equal to 10 raised to power 8 operations, then you may get a TLE. Since here it is lesser than 10 raised to power 8 operations, then your solution will be accepted. So also I will be also providing a link describing how the time complexity of accepted solution varies according to input size. So let's quickly dive into the coding part. There you will be able to understand the problem solution in a much clearer way. So basically the approach I have told you will not change. Just it's the implementation that is remaining. So this DSU, we have used two optimizations in DSU. The link that I will be providing will be explaining you. This is the link. Disjoint set union. It will be explaining you each and everything and the optimization that we have used. So basically, what are the optimization we have used? We have used the path compression optimization, and uh, another optimization is used by union by size or rank, and union by rank. I would have explained you the DSU data structure, but it will take a separate video. And if I go on explaining you in this video, it will increase the length of the video. So if check this article out, and if you are still having any doubts, feel free to ask them in the comment section. Basically, check all the articles that I'll be providing the links for. So this is a standard DSU with two optimizations. So what we have done is we will form a new 2D array or say vector for preserving index of the edge. so that we can return it as our answer. Basically, the answer is expecting you the indices of the edges. First part, it will be the critical edges, and these will be the pseudo-critical edges. And these values are nothing but the indices of the edges according to this edges array. So the indices of the edges in the given array edges we will be preserving. So firstly, we will be adding whatever is given to us, the edge and their weight. Then we will be adding their index also. Once we are done with it, we will sort the edges according to their sort the edges according to their weights in increasing order. So then what you will do is you will form a MST and check its weight with the help of Kruskal's algorithm. Kruskal algorithm implementation uses disjoint set union. So we will be implementing the Kruskal's algorithm. Uh, those of you who are new to this kind of implementation, you need not have to worry about it. The implementation of the Kruskal algorithm using DSU is also given in the link that I will be providing you. As you can see, the implementation part is also covered here. You can check it out. Basically, you will be forming a MST and checking its weight. Then for each S, you will check if it is critical or pseudo-critical edge. For checking the critical edge, what you will do, you will try removing it from the minimum spanning tree. If the critical, if it is critical, then it will result in disconnected spanning tree or increase in the weight of the minimum spanning tree. So if the spanning tree becomes disconnected or the number of nodes in the new spanning tree that will be found is lesser than the number of nodes in original spanning tree, then what will happen is this node will be a critical node. In these cases, the edge, sorry, it's not the node, the edge will be a critical node, critical edge. So if that's not the case, you will check for pseudo. If that's not the case, check if it is pseudo critical edge. What you will be checking is after forming the MST, what we will do is For pseudo-critical edge, it will be involving forming a minimum spanning tree with the current edge and all other remaining edges. And then checking if the weight remains the same and the graph does not become disconnected. Minimum spanning tree does not become disconnected. The number of nodes in the old spanning tree should be same as the number of nodes in this new spanning tree, and the weight also should be remaining same. Then if that's the case, if this condition satisfies, then the edge is critical edge. And at last you will be returning your result. So this is we are storing the index of the edge in the results array. So if you are still having any doubts in the solution or any of these links that I will be providing, minimum spanning tree, Kruskal's algorithm, disjoint union set, and if you want to further explore, you can explore what Prim's algorithm is, how it makes a minimum spanning tree, and what is the difference between Prim's and Kruskal algorithm. If any, if among any of these you are having any doubts, please feel free to ask them in the comment section. I will be more than happy to answer them. So that's pretty much it. Thank you for watching. Thanks.